Okay, so now that we have a good grasp on Gaussian elimination and some general properties of matrices, we're going to look at different ways of solving systems of linear equations. And we've already covered Gaussian elimination. So now we're going to talk about the two other methods that are commonly used. And there are actually others. Um, the one method I left out, which is a little advanced, but we may cover it next week, is the Cholesky decomposition, which is actually the best of all these methods. Okay, let's do a little overview and look at the pros and cons of each method. So the pros of Gaussian elimination is it can be used for any matrix of any dimension. The number of flops for an n by n floating point operations is roughly on the order of n cubed. That's roughly the same as the other methods, with a few caveats, but that is considered not bad. Okay, so it's relatively efficient and it's very general. The cons are that it can be unstable, but the biggest drawback of Gaussian elimination is that we have to redo it for every column vector b. So if I want to rerun and get the solution for the same system where I just changed the right hand side, it's going to be another n cubed operations for that system too. So where LU decomposition comes in is it basically has the same pros and cons as Gaussian elimination, except for the fact that when we change the right hand side vector, we only need n squared flops. Okay, and depending on how we choose the pivots, some people argue it's actually on the order of n log n. Okay, so it's more efficient and it's a little more stable too. And so when MATLAB or whatever program you do solves a system of linear equations, it almost always uses LU decomposition. Okay, it doesn't compute the inverse generally. The last method is called QR decomposition, and QR decomposition is special in the sense that it can be used for overdetermined systems. In other words, systems where we have more equations and unknowns. And we get this when we do, for example, least squares fits, okay, or regression. And so it's definitely better there. It's also a little more numerically stable because it's based on a method known as Gram-Schmidt orthogonalization, which we're going to talk about next week. Okay, so this kind of puts the different methods in order. We can always use Gaussian elimination, but if we want to be more efficient, we use LU decomposition. And if we want to be very stable, or we're working with a system of overdetermined equations, we're going to use QR decomposition. Okay, so let's take a look at triangular matrices, because the LU refers to a lower triangular and upper triangular matrix. And so we're going to define a lower triangular matrix as any square matrix where the elements above the diagonal are 0. So it looks something like this. And an upper triangular is a matrix where all of the elements below the diagonal are 0. Okay? Now there are two important properties about upper triangular matrices. The first is that, lower triangular matrices, sorry. The first is that the set of lower triangular matrices are closed under addition, multiplication, and inverses. And it's not a bad idea to stop the video and convince yourself that you believe all three of those things. Okay. Not all lower triangular matrices have inverses, but if they do, they have to be a lower triangular matrix. This is a very important fact. Okay, another thing to realize is that all matrices for elementary row operations are lower triangular. And again, this is a statement that you should prove. Anything in blue is something that you should prove. You should definitely make sure that you understand this, that you're convinced that all of those different type 1, type 2, type 3 elementary row matrices are always lower triangular. I'll mention in passing that the statement about closure is also true for upper triangular matrices. And you can show that just by taking the transpose of a lower triangular. Automatically it makes it upper triangular, right? And so all those same statements have to be true for upper triangular too. Okay, now here's the rationale for LU decomposition. A fundamental fact that we're going to use is that every n by n matrix, which we're going to call A here, can be decomposed as a product of two matrices. L is the lower triangular and U is an upper triangular. And the reason why that's true, we can prove that quite easily, because if we consider doing elementary row operations on A to get it in row echelon form, we know that the final product of row echelon form is always an upper triangular matrix. And so we can represent that situation as shown. We're gonna have, say, small p elementary row operations, represent them by elementary row matrices, and we can get the upper triangular by applying them to A. Now we said before that the elementary row matrices were all invertible. So we can easily put all of the elementary row matrices on the right hand side just by multiplying by the inverses in the right order. And remember that we said that the elementary row matrices were all lower triangular, okay, and lower triangular matrices have inverses that are lower triangular, so all of these inverse matrices are lower triangular, and lower triangular matrices are closed under multiplication, so this product is a lower triangular matrix, and that justifies us saying that A can be written in this form if it's a square matrix. Okay, how do we use that? Well, here's how we use it. We start off noticing that when we get the row echelon form of our matrix equation, which is ux is equal to y, if I multiply both sides by L, okay, I'm going to have LU times x is equal to LY. Well, I know that LU is A and LY is B. So notice now that I should be able to solve Ly is equal to B for y, because this is basically just going to be a back substitution, right? So I can solve for y, and once I have y from this lower triangular matrix equation, then I can simply go back and I can solve for x also using back substitution. I get the y that I obtained from the solution Ly equal to B, plug it in the equation ux is equal to y, and solve for x by back substitution. And that's the idea behind LU decomposition. Okay, so the key steps are basically that we're doing Gaussian elimination, but we're keeping track of the operations and constructing the elementary row matrices associated with them. So at each step of the Gaussian elimination, we're going to form two matrices. First, we're going to find the elementary row matrix for the elementary row operation, and we're going to be constructing U with that. We keep on applying the elementary row matrices. We're eventually getting it down into row echelon form. But at the same time, I want to form L, and you remember what L is. L is the product of the inverses of the elementary row matrices. So I'm finding the inverse, and I'm constructing L by just multiplying by the inverse of the elementary row matrix on the right hand side. Okay, now I have L and now I have U, and now I simply do back substitution. Okay, one little caveat you have to be really careful about, and this is what complicates the algorithm, is the choice of the pivot. So first you have to make sure that no pivot's 0. In other words, if in the 2-2 position I have 0, I have to make sure that none of the rows below it in the second column are non-zero, because if they are, I'm going to exchange them. Okay, so that's an important point. So we may have to do a row exchange. Some people make a big deal about the choice of pivot, and there's a little bit of controversy surrounding that. Supposedly people have proven that you should take three random pivots for each column, if there are 3, and randomly choose one, and that causes better performance. In any case, once we get L, we just do back substitution using b to get y, and then of course once we get y, we simply take ux is equal to y and we do back substitution with u to get our solution for x. Okay, and so we can code this up. It's not that difficult to code. And as an exercise, I'd like you to write some pseudocode for performing an LU decomposition. Your input should be an arbitrary coefficient matrix and a right-hand side vector b. Remember, the coefficient matrix has to be square, has to be an n by n, and b has to be an n by 1 vector. And your output should be the solution and the two matrices u and l. And you should verify that L times U is equal to A. Okay, that's all for LU decomposition, but I would seriously urge you to try writing that program because it's kind of a good exercise in how to learn how to work with matrices and also how to do LU decomposition on your own. It's quite useful because a lot of techniques are actually based off of this. Okay, in the next video we're going to talk about eigenvalues and eigenvectors.